can easily lead to state 27. So that's something we call as the state value, which we had a former designer too. And we also talked about state action value function. And this is basically saying if you're at state 27 and move towards the right, that's a good thing. And if you are state 21 and the action is down, that's also a good pair. So we can assign those values to the pair of state and actions. And if you have a complete list of the values of the state action pair, then for each given state, we can basically pick the action with the highest value, and that is basically going to tell us which action to make. So then the problem is, or the question is, how do we actually use that information and make it flow backward? So we talked about lots of different things, but the main essence lies within, where is it? Within this Bellman function. So this is the important thing in reinforcement learning. So the Bellman equation for MRP, which was Markov reward process, or MDP, which is Markov decision process, it simply says the value of a certain state and action pair equals the reward or expected reward you're going to immediately get plus the expected value of the future reward. That's all this Bellman equation is saying, nothing more than that. It is actually kind of very obvious thing. And the important part was here. So this equation, the right-hand side is saying the for a given, assuming that the policy is optimal, then what you expect, which is on the left, is the same as the best you can get. So let's talk about that a little more. So on the right, we have this max operation over A prime. So among all possible actions you can possibly make at S prime, this right-hand side is going to be the best one. And that is going to equal to what is probabilistically likely to happen given the policy. So this is a, conditional probability to transit from S to S prime. And for each S prime, we are going to calculate the state action value. And we're going to sum that. And that means this sigma is nothing more than a weighted sum of this Q value. And that basically means we're talking about the expected value of this Q value. And this equation is saying the expected value is the same as the best value we can get. And that'll only happen if this is expected to do the best thing. If the policy is optimal, then what is expected is the same as what's the best. And that's all this equation is saying. In that case, we can replace this term right here, the future value, by this max term right here, which gives us the Bellman equation for the optimal policy. So these two are general Bellman equations. That is just saying that value equals present value plus future value. And this equation only holds for an optimal policy. And that's what we are going to use to train the network in a reinforcement learning setting. So what we said was, we know that this equation, this part has to be 0 for an optimal policy. And that makes us think that any deviation from that could be considered as an error. So we're going to define a loss function like this. And we can optimize, or we can train the network so that this loss function is minimized. So we're going to update the parameters of the network, which is data, to minimize this loss function, which represents the deviation from the optimality condition given by the Bellman equation. So once we have the loss function, maybe we can just gradient descent to minimize this loss function, and then that'll hopefully take us to the optimal Q function. So that's actually one way to interpret that. So assume that if we know the true Q function, we do not know, but let's just assume that we knew it, then what we would do is we would train our network such that the difference between these two would be minimized. And if we define that as the loss function, then the gradient, the gradient would look like this. And we do not have this true Q value. So we said we're going to let the information flow backward. So we're going to use this term. And instead of this, we're going to use what we get from the future term, which is this, and use that to update this. So that's the main idea of this update. There are also other possible ways to interpret this, but again, this is one way to understand this update equation. So by doing so, we can train the network. So that's the mathematically, that's the end of the story. But if we really want to train a network, we actually need some other things. So that includes, where is it? Oh, we actually have to let the agent interact with the environment to collect these sets, which is called as an episode. And if we do not, if we start with just a random agent, then the action that comes out of it will be almost certainly very bad. And that means the episodes will not have any good data. And that means we cannot collect good things. I mean, the training data is very limited because it's going to do the same thing again and again and again. And it's never going to be close to the optimal actions. So to solve that problem, we have to not just follow the policy, which is not optimal. And that leads us to an idea of doing some random actions to collect the data. So instead of always following the agent, instead of always following the action that came out of the Q network, we sometimes can choose some random action to collect the data. So we can actually do the random action with some probability epsilon. And in that case, we call it an epsilon greedy algorithm. And another thing is that if you actually generate an episode, these SAR, these are going to be highly similar. I mean, the state are not going to change very fast. And that means if you just use these, let's say, for example, these three as the training data, it's not very good because it's not really random enough. They are kind of similar. And it's like, if you recall, in the linear regression problem, let me see where I have the pen. Oh, in the linear regression problem, we talked about one of the things that if we had some data points like this, what we want to do is to randomly sample these points to do the gradient descent. And what we don't want to do is to group these closed samples. And that's going to be very bad. If we update the gradient descent from this, it's going to look like this. From here, it's going to look like this. I don't know, this. So that's not so good. We want to make the samples as much as random as possible for using that for update. So for that, what we can do is we generate this data and save those in a buffer. Buffer simply means some sort of memory, and then randomly pull out those from the buffer and use for update. So what I'm saying is, instead of simultaneously generating the episode and using that episode for an update, what we can actually do is we generate the episode and we store them in a buffer. And instead of using those sequentially for updating, we just randomly sample those and use those for update. So that's the replay buffer. And combining that gives us the DQN training algorithm. So we start with initializing the replay buffer. That means just memory allocation, not doing anything. We define a Q network, and we're going to generate a target network, and then the iteration starts. So what's going to happen is, for some probability, we're going to choose the agent is going to choose a random action, and in other case, it's going to follow the Q function and perform the action and get the reward, collect the reward and the transition to the next state. And that becomes a transaction. Transaction means just a set of S, A, R, and next S. So we're gonna save these in the buffer. And the next, and then what we do is we sample a mini batch from the buffer and do the update. And then go back to the environment and generate another transaction, store that in the buffer, and do the update repeat. So that's the bottom line of deep Q learning, which is what we are going to practice today. Actually, today's material is not really about activity. So the thing is, I thought that most of you would be using your Colab resources for your final project, and that means you may not have enough Colab availability to run something else. So instead of doing that, I think we can just go through together on my thing, and then later maybe you could take a look on your own after the semester. All right, so let's start with the note 11A. So this is just about looking into the environment. It's not really doing anything in terms of reinforcement learning. It's just installing and loading things to see what kind of environment we are talking about. So here we start with installing some libraries that are required for inline visualization, and also install gem, which is what we need for, which is basically the set, which is basically a library that contains multiple games we can use for reinforcement learning. And we are also going to import Pi virtual display for visualization. And here we start importing gem, again, which is the library that includes multiple games for reinforcement learning. And we can actually choose one of these games. And for some reason, when I wrote this code, all of these were working fine. And I realized that for some reason, I think there was some library update, and not all of them are working now. I don't really know why, but we can go with cart poll right here and just run it. And the environment instance is now created. And let's take a look at the single frame. So this is how it looks like. This is basically an inverted pendulum problem where you can move this black box while this brown stick may rotate and fall over. So your job here is to move this black box so this brown stick doesn't fall over. So if it's tilting toward the left, you may want to move this black box to the left so that it could balance. And if this is tilting towards right, you may want to move the black box toward the right. But if you move it by too much, then it'll fall over the other way. So it's all about keeping the balance. All right, so this is how an environment looks like. And we actually need so very many libraries because these are not related to the learning. These are just for visualization. Let's not worry too much about it. And here we have a custom function to convert an episode into a video so we can actually see things happening. And here we are going to generate an episode. So this one is actually pretty short. It may look like it's keeping its balance, but what's really happening is when it falls, the last scene is not generated. So the scene after this frame is game over. It failed to keep the balance. So that's why it ends here and just repeating this very short video. So it was, how long is the thing? Yeah, in any case, it's super short. It fails to keep the balance and game's over because we are using a random action or random agent here. All right, so here now we are actually going to do some reinforcement learning and see if we can keep some balance of this inverted pendulum. So again, lots of libraries, and we're going to generate the environment instance. And here is our CoE network. So this specific environment just gives you a vector with 4 values, 4 entities as the state. So what I mean is, this is the framework for reinforcement learning. And here, the environment is supposed to give the state to the agent. And that state consists only of 4 numbers. So the environment is not giving the whole video to the agent. It's giving just 4 numbers to it. And that 4 numbers is actually a vector that consists of the position of the cart, the velocity of the cart, and the angle of the pole, and the rotation angle, or the, how do you call it? Angular speed of the pole. So only those are given to the agent. So that's what the CoE network, the agent here, is taking as the input. And the output it has to generate, the action, has to be either left or right. So the output is 2-dimensional. So 4-dimensional input, 2-dimensional output, and we just have a very simple MLP as our CoE network. It's super simple. And here we have the update part, which, if you take a look, this is not very complicated. This part is just about randomly sampling a transaction. Again, by transaction, I mean SASR or SARS, the set, this thing. We sample that, and where's the equation? And simply calculate this loss value right here and do the gradient update. We calculate that. So we calculate this, and we have our loss function here, and do the gradient descent update. That's pretty much it. It's not very complicated. It's actually very simple. And here we have some hyperparameters that include the size of the buffer, discount factor, which is gamma, and the number of time steps, and the target interval. Well, this is a little bit beyond the scope of what we are doing, so let me just skip this part. And then we have this CoE network. We create the CoE network instance and optimizer as well. And we start with the untrained. Oops, this was actually trained one. I actually trained it earlier. Let me do it again, actually. So this is not trained at all. So the game ends after 8 time points. So it was able to keep the it was able to avoid falling over only for 8 time points. After that, it failed. And the goal here is to keep it not fall over for as long as possible. And that's happening right here. So what we do is we have the outer loop, and we generate an episode starting from t=1 to the maximum time step. And if the random number is smaller than an epsilon, which is 0.01 here, we choose the random action. So we are talking about this part. And if not, we choose the action that comes from the our agent. So that's right here. And give that action to the environment, and that environment is going to give you state and reward, and that's what we need. And using that, we are going to calculate the loss function and do the update. So that actually directly goes to the buffer. So this is the buffer, and this update queue will randomly sample some data points from the buffer and update the network. And yeah, that's almost pretty much it. and the training is happening right now in real time. And the reward, the average reward we get is going better over time. Okay, so that's pretty much it. And here's another one, which is almost the same as 11B. The only difference is that here, the only thing you can see is this graph. So it doesn't look very exciting. The example we have here is actually 99% the same. I mean, if you take a look at the Q network, it's actually exactly the same. And the only difference here we have is we just have this for visualization. So here you can see what happens with this visualization part. We can see what happens. So earlier, it failed after 8 time points. And here, it was able to retain the balance for more than 260 time points. So you can actually see that from its own experience, it learns how to move left and right to be able to keep the balance. And that's the main idea of reinforcement learning. All right, so I think that's pretty much it for the reinforcement learning practice. And let me just add a few other things. So as you may have seen, the submission page is now there on both KLMS and also on this, what do you call it, CoDA lab. So I noticed that some people have started to submit their results, which is very good. And please do so before too late, even if you're not totally satisfied with what you are getting right now. Okay, so that's almost it. And before I finish, let me just say a few other things. So this lecture note is actually from the very first lecture of this course. And we set the goal of this course as basically, my goal was to convince you that AI is not difficult. And from theoretical aspect, it's pretty much the same as polynomial curve fitting. It's not so much different than this. So my goal was to convince you these two things and to provide the basics and fundamentals of AI. And your goal was to understand the basics and fundamentals of AI and to be able to design a simple AI. And that was pretty much your goal. So I really hope that that goal was fulfilled fulfilled with this course. And the intention of this course is not to make you an AI expert. The intention is to convince you that it's not so difficult and to give you some guidelines for your future study if you want to pursue your study in AI or if you want to use AI for some other purposes. So yeah, I really hope that's the case for you. And I wish you the good luck with your final exams and also the final project. All right, that's pretty much it. And this is the very last lecture. So I guess we could finish after taking any question if you have.